Hello, everybody. I'm Olaf Strammer, and I'm part of our industrial quality team. This is the overview webinar. We want to start with the global trends, benefits of quality testing in the industry. We talk about application examples. Then I will show you our overall portfolio and introduce our three types of applications, which is end-of-line testing, non-destructive testing, and process monitoring. Yes, but now let's start from the beginnings. So let's at first have a look at the global trends for industrial manufacturing. What makes industrial manufacturing today? I hope, or I think you all are more or less involved in industry and manufacturing and quality at the production line. And so these sentences are not, or these words are not new to you. We talk about deliver excellence. We talk about going green. To be responsible regarding the environment is important today, even for production, even for automotive, even for other industries. Then, of course, we live in a global world. Industrial production, manufacturing is also global, and standardization is a typical thing of industrial manufacturing, and it is even more important if you think globally. Then very important quality. That's why we are here today. We want to talk mainly about quality of industrial manufacturing, which is an important key factor to be successful, to be able to survive in this global world, to deliver excellent products, and even to deal with our environment. Yes, what does it mean more in detail? If we talk about deliver excellence, then we talk about how good is our production. How much does the production cost? What is the price? What is the profit behind this? And you all may know that if we have to do a lot of rework, scrap, if we have product failures, if we, knocking on wood, have recalls, then it can have quite a big impact on the production and even on the company. If you talk about going green, then we see some quite interesting streams currently, especially in automotive. This is engine downsizing, but more important is this electric mobility. We talk a lot about electric vehicles. That means the electrification of the cars have big impact on quality, especially on sound quality. It has also impact on another point, lightweight design. For an electric car, the range is a quite important parameter, and you can have a high range of a car if the car is lightweight, so that you need less energy to move it. That means going green, using less energy is a point, and it also has impact on the quality testing. That means if you have a light structure, then the stress on the structure is maybe higher than if the structure would be more heavier, more bigger or more traditional. And so quality assurance of these light structures, light car bodies is maybe even more important than it was in the past. Then if you talk about standardization again, if you look at the automotive companies, we today talk about global platforms. That means even if the cars are more or less customized for a certain country, if you buy a car in South America, North America, in Europe and Asia, this car from a certain brand will base on one platform, and this platform is used globally. It is a little bit tailored for the certain countries, but the platform itself, this helps to accelerate the production, to make it cheaper, to make it faster, to make it more profitable all over the world. And it also requires, of course, global standardized quality measures, so that person which buys a high-class car in Asia gets the same quality as if we would buy the car in the US. So standardization is also a very important thing for the quality. And of course, we talked a lot about quality. It's crucial across the organization. We do not talk about insulated points where we check the quality. The quality is more or less related with the complete manufacturing process or even with the complete life cycle of the product. It starts at the development. We talk today about production, and it also will have impact on the lifetime of the product itself. So that means also the faults that we want to find at the end of line test can impact the lifetime of the product. So those are all points that we take into account. Here are now some examples. If you talk about deliver excellence, then here as an example, if you talk about an industrial production line, then today, it's quite important to deliver the right product at the right time. It is called just in time. So if you configure a car at the car shop, then this car consists of certain components, and every car that is configured can look a little bit different. So there are thousands of modifications, thousands of different types of cars that can be built on one production line, and even the components like the IC engine that you see in the video here has to fit to the production line. That means such a just-in-time production produces exactly that component that is needed. And if the quality does not fit, if we have to sort out items, then this sequence is destroyed, and it will produce quite big costs to get in sequence again. So to avoid this, a 100% quality inspection is implemented usually on such production lines, where every part is tested, where every part is inspected, and where every faults that are detected are identified. What you see here, for example, on the picture is an engine plant in Austria, and to 100% these engines are tested with an ANOVUS system. That's what we are talking about today. That means robust and reliable end-of-line testing is crucial to be able to deliver at the end. If you're talking about Go Green, this is an 8 HP gearbox. These things are quite complex, lightweight designs. And of course, if there are many parts built in such a transmission, many things can fail. And of course, they have to be detected. That means quality control requirements are rising. Innovative sound and vibration-based analysis helps us to detect faults that aren't able to detect with other techniques. For example, damages of gears. It can happen if such a gearbox is mounted. It can happen that a gear falls down, that it gets a small damage. You will not see this in torque signal or in the temperature or speed or profile or wherever. It's only detectable if noise or vibration is measured. And this small damage can have influence or impact on the lifetime of the transmission. The small damage becomes bigger and bigger. A tooth breaks, the transmission blocks, the car breaks down. And this can happen in the first 1,000-2,000 miles of the car, which is not so funny for the car producer, or it can happen never if we detect these faults at the end of line test. Or if we talk about global standardization, end-of-line testing is standardized globally today. This is not only a question of the test system itself, it's a question how the test system can be integrated in a global quality management system. Here we are talking about central databases, global quality management databases, global definition of quality measures, of metrics that have to be used worldwide, that have to be on the tailored products that are used all over the world, but they have to assure the same quality all over the world at the end. And of course, if you talk about quality across organizations, then we not only have to take manufacturing into account, but also the other departments of the company. It starts with the research. At the research department, of course, everybody takes care that the noise quality, the vibration quality of the part is quite okay, that also the overall quality fulfills the requirements in the sense that the lifetime will be reached of the component. And this, of course, has also impact on how it is possible to manufacture this item, especially if we talk about new ideas that have influence on research and development. The new ideas have to be put into production and have to be able to produce. And therefore also quality management can help to increase the stability, how a certain product can be built. And the statistics, the information that we earn at the end of line test bench can also have influence on research and development. I personally was involved in the last years also in installing our systems on the test benches, on IC engine test benches, transmission test benches, and it happens several times that we work together with research and development people to make the product better, to see what really happens in production if all the tolerances of the automatic production lines are used. Do the parts look as the researchers or developers had this in mind, or are there tolerances that do not fit to the design? And in the end-of-line test, we can produce thousands, millions of data sets to find out what is the real statistics of the production. And this also helps us to find the most interesting points or the most important points to increase the production quality, to find out what is the real root cause for the majority of the faults and how can we avoid this fault. And this has also impact on research, and in some cases the construction will be changed, the design will be changed of a part so that it's easier or even cheaper to produce it and to produce it even with a good quality. That means this is a kind of circle, and at the end of line test or at the industrial test, we are a part of this circle to check the quality, to make a good statistic, to provide the data, to provide information about root causes so that research and development can improve the part from loop to loop. It's a kind of iterative process that also can be controlled by end-of-line quality testing. So you see not only the manufacturing plant is involved in this process, but at the end, the whole plant. So this is more or less a short introduction. If you're talking about industrial quality testing, we all want to help you to increase the quality of your products, to help you to make the best profit from the products that you sell, that you develop. Yes, and on that field, we have several applications, and this slide shows what applications we at Siemens IQT, Siemens Industrial Quality Testing, can provide to you as a producer of items to help you to increase the production quality. At first, this is end-of-line testing. That's the thing, took the examples out. The typical application is that you have a production line where a certain kind of item is produced, like an IC engine, an electric engine, a transmission, electric drive unit, even an assembly of something that moves, like a windscreen wiper, a door lock mechanism, or even out of automotive, it can be the motor of a washing machine, it can be the compressor of a refrigerator or whatever. Everything that moves, that makes sound, that vibrates, is a typical test item for noise and vibration end-of-line testing. And the goal of the testing is to detect the faults, but not only to detect them, also to identify them. It's quite important if you have complex items like this 8-gear transmission that you see here on this test bench. It consists of some 100 components, and if test bench only would say this item is wrong, this item is loud, then it would not help, since the transmission has to be repaired. And to support the repair, to make the repair as effective as possible, a good fault identification is important, is crucial. Or we can also talk about money. Maybe if a transmission is delivered to the customer which has a fault inside, it will cost the plant some $1,000, let's assume $3,000. On the other hand, if we find a fault and we send transmission to the repair loop, it's also not for free to repair it. But if we only would say this part is not okay, then maybe one operator is dealing with the transmission for 2 or 3 days to find the root cause of this fault. And so you do not save money. At the end, you also pay $2,000, $3,000 until you found the fault. But if we can do a good fault identification, we can reduce the time that is needed for repair to, let's say, 2 hours or 3 hours, and then you only pay, let's say, $300, and you decreased the cost for this faulty transmission by a factor of 10. And of course, you get much better reputation for your customer since you did not deliver bad gearboxes. So this is the way how end-of-line testing thinks. We want to increase production quality, we want to reduce costs at the end-of-line test. We want to reduce the expense that is necessary to repair the items, and therefore a good fault identification is necessary. And of course, all these things run completely automatically. The whole test is designed for a complete automated test run. The next example is non-destructive testing. Here we are talking about resonance testing. It's a quite simple method. Maybe you take a glass, you hit the glass, then you hear a sound. And this sound is generated by the resonances, by the answer on this hit. And the resonances can tell you something about the condition of this glass. That means if the glass would have a crack, then it would be clearly hearable. It does not sound clear and does not resonate for a long time. It is clearly hearable that there's something wrong with this item. And that's the same principle that we use here. We take a part, we hit the part, we listen to the sound, and if the sound is okay, then we say, yes, part has a good quality. If the resonance parameters change or differs from the normal production behavior, then we say there's something wrong with this part. This method has the advantage that it is quite fast and it can be optimized in a quite good way, and it's even a cheap method. What you see on the picture is a belt pulley of an electric power steering for a passenger car. This part is made of aluminium powder metal, and the cost of this part is about $3, something like that. But it's safety critical part. If this part breaks, then the result will be an accident. your steering blocks and you cannot steer the car, and this is quite dangerous. And so 100% of these belt pulleys have to be tested, but they are cheap, so the test has also to be cheap. The test should cost maximum some cents per part. And so this resonance testing is quite a good solution. Hitting a part, listening to the sound, telling it's okay, it's not okay, it's a question of seconds. We can have cycle times between 1.5 seconds and 10 seconds for such parts. And so it is quite easy to do a 100% test with this method. And this is possible even if we talk about quite cheap parts like these pulled bellies. Also forged parts like crankshafts, camshafts can be tested, and even car body parts. Car body parts is quite a typical application for such a measurement technique, since single part of a car body is also quite cheap. It costs some dollars. But if it's welded together to a whole car body, then the car body costs, let's say, $5,000, $10,000. And if there's one cracked part, the whole car body can be thrown away. And so it's crucial to check single parts if they have cracks, if they have faults inside, to be sure that the whole car body is free of faults. This is also a typical application. Yes, and the third group of applications that we provide is process monitoring. The way to do this is quite simple. For end-of-line testing, for non-destructive testing, we take the noise and the vibration emitted from the device under test to extract information about the quality. And this is also possible for a process step itself. If a certain process step works, it produces a certain fingerprint of vibration and sound. And if this fingerprint changes, we know something went wrong. Something was different in this production step than it was the last 500 production steps before. And it's very likely that this difference leads to a quality problem. So our Novus system is also able to supervise the noise and the vibration emitted from processes, from machines, to give an alarm if something went wrong. What you see here is a manual application. The parts that are built here are insulators for high voltage power lines. They have a glass fiber bar inside and an aluminum part crimped on this glass fiber bar. And during this process, the glass fiber bar can break, and our sensor detects this typical noise that occurs if a glass fiber bar breaks and sets an alarm if this occurs. This is such an application for process monitoring. Those are our applications. Now let's start at the end-of-line test. I will show you some examples what we are doing on these three applications. The end-of-line test examples are internal combustion engines, transmissions, and electric drive units, which is more or less the future in my point of view. So let's start with the good old IC engine. Noise and vibration-based quality testing can be used at the end-of-line test, which today in volume lines is mostly a cold test. That means the engine is turned by an electric motor, by a dynamometer, and the test bench measures torque, pressures, temperatures, and can give a rating about the overall quality of the engine. But some of the faults are not visible in the torque, in pressures, in temperatures, in sensor readings, but they are visible in the noise and vibration emitted from the device under test. So a full automated 100% NVH test can help to detect faults that are not detectable by classical methods. So today, a typical cold test is using NVH, and Novus system is a part of the whole test bench that does the NVH part. And what you see here on the slide is a list of typical faults that can be found. If you are an IC engine producer, you may know some of these faults. I can shortly go through the list. If we go from top to down through the engine, then we start at the camshaft. We can find surface defects, we can find chatter marks. If you look at the valve train, typical thing for the valve train, it can rattle. We can detect rattling, can identify several sources of this rattling. Today, an engine at the test bench also is equipped with several pumps, like high pressure pumps, membrane pumps. They can have issues that we can find. The oil pump can make noises that helps us to find faults with the oil pump. Turbocharger can make noises if they are damaged, if the geometry is not right, if they have unbalance. The timing drive, even if it's a chain or a belt, can make noise, can hole, can rattle, which can be used to identify quality issues like not working chain tensioners, damaged wheels, wheels not mounted in alignment. The same for tooth gear drives, tooth damages, surface defects can be found. Balancer shafts which are not mounted in the right way, vacuum pumps with surface defects, piston crankshaft defects, all these things are typical things that only can be measured or only can be detected when noise and vibration is analyzed. The next part in the powertrain is the transmission. The challenge is the same. On the one hand, the noise quality of a transmission is quite important. On the other hand, we also, or our customers also do not want to deliver transmissions with faults that would lead to a breakdown. And so the end-of-line testing system has to detect both. It has to detect noise and vibration as a quality criterion, and on the other hand also defects in the transmission that would lead to a break of the transmission to assure that only 100% perfect transmissions are leaving the production line. And this is also done by a fully automated NVH test system at the end-of-line test bench. The NVH test usually is integrated in the overall functional test so that no extra testing time is needed in most cases. And the benefit is that even every single transmission is tested for noise and vibration. And those are the thoughts or the issues. Of course, if you talk about transmissions, we mainly talk about gear issues, gear noise from bevel gear sets, spur gear sets, gear defects, ghost orders. Those are so-called machine orders. If the machine that forms the shape of the teeth makes resonances, then chatter marks can occur, which lead to ghost orders, noises that are there but should not be there. They can be detected by an end-of-line testing system. Bearings can make noises, they can have damages, they can make overall noises. Also shifting elements like clutches, like shift levers, like synchronous rings, all these things can make noise. And also oil pumps, unbalances of shafts. So all these faults, again, typical faults that cannot be found by classical methods like measuring torque, measuring speed profile, but can be clearly detected by measuring noise and vibration. Yes, and last but not least, we talk about electric drive units, combination of a very simple transmission and an electric motor, and sometimes a little bit of electronics. And yeah, the challenge is nearly the same. On the one hand, the noise plays a big role. Even in electric cars, the electric itself is quite silent. On the other hand, it produces new types of noises that are unusual for the people, for the driver of the car, or even for the people walking around the car. And so the quality demands on the noise emitted by an electric car is quite high. And this is not only noise emitted from the motor or from the gearbox, but also noise emitted from the electronics. This typical PWM noise, electronics noise, always now becomes common for electric cars, but it's a noise that is very annoying. And so the producers of the cars try to avoid this, and therefore it has to be measured at the end-of-line test bench. The challenge is the same. We have to find noises and we have to find faults that have influence on noise. But the frequencies and the behavior of the noise now is different, and the system has to adapt to this. We need higher bandwidth. We need other analysis functions to be able to clearly identify this frequency converter noise and to rate this. And at the same time, we have to measure the noise and vibration from the transmission or from the motor. So the system has to be adapted to measure at the end-of-line test for electric drive units, and the requirements are a little bit different. So if you look at the electric motor, we have to deal with unbalances, bearing noises, bearing defects, rotor vibrations, tumbling of the rotors, eccentricity are very interesting measures, and also pairing of magnets, quality of coils, all these things, even the quality of the electronic, the insulation of the coils, the damping of the coils. This is quite interesting for end-of-line testing. And of course, if you look at the gearbox part, chatter marks, gear defects, tooling, mounting faults, everything can have influence on noise and vibration or quality in general, and this has to be detected by the end-of-line system if it has influence on noise and vibration. Yes, this is something that we can do at the end-of-line test, or that a SimCenter Novus can do. Yes, and now we talk about the next point. You remember end-of-line testing, non-destructive testing, process monitoring. Now some slides about process monitoring. Here are some examples. This is a mounting machine where the connection rods for stabilizers are mounted. They produce these connection rods for stabilizers for the car. They have ball joints on both sides, and they consist of a steel ball which is pressed into a ball cup made of plastic. And during this process, the cup can break. If the parts are not in the right position to each other, the cup can break. And this break will lead to a non-functional connection rod, of course, but this break is also hearable. So we installed a microphone at this machine. The microphone listens to every single mounting step. This can be thousands per day. I think they mount one part every 10 seconds, something like that, or even faster. And if a breaking of such a ball cup occurs, then the system sets an alarm and the affected connection rod is sorted out. This is a typical example of supervising of a process. Another example you can see here on the picture, that was the test measurements. That's why the two sensors that you see here are not mounted in a very industrial way, but afterwards the cable, the wiring has been done a little bit more professional. But you see here a so-called calibration press. On this press, valve seat rings are calibrated. Those are the rings that are built into the cylinder head where the valves are sitting in. And this ring, the diameter or the geometry of these rings have a very, very narrow tolerance. And to achieve this, every ring is calibrated on a so-called calibration press. The rings are made from powder metal, those are sintered parts, and they are produced a little bit, some microns smaller than they should be. And on this press, they are widened, this tool, in a way that they exactly fit from their geometry. And during the process, it can happen that the ring breaks. What you see on the lower picture is such a crack that can occur. And if this crack occurs, a certain noise occurs, and this or vibration occurs. And this vibration is recorded with the two sensors and analyzed by the Innovus system. And if we detect such a crack, then we set an alarm and the part is sorted out again. And you can imagine that such a press makes a lot of huge vibrations, huge noises. And in this shop floor, it's not very silent. And even under these conditions, it's possible to detect the noise that occurs if such a small crack occurs at this part. And then the last example for process monitoring, this is detection of wrong mounted electric plugs. It's an IC engine again. The IC engine may have spark plugs. And top of the spark plugs, the coil is mounted and the coil is connected with an electric plug. And this electric plug has to be really clicked in so that the plug is locked. If the lock fails, then after 200 miles, because of vibration, the electric plug falls out and the engine stops. And this is a quite annoying fault that happens from time to time, and it's very annoying for the car producer. You buy a new car, drive 300 miles, the car blocks because of such a small issue like a not connected electric plugs. It does not give a good picture about the quality. So it has to be avoided. The question is now how to detect this. One possibility is to listen to the click that occurs if the plug locks. And we do this with a microphone. If the click occurs, everything is fine. If no click occurs, the operator gets an alarm that he has to check the plugs. And so it can be avoided that plugs are not connected during the production line. Yes, those are 3 examples about process monitoring. Now also some slides about non-destructive testing. At first, I want to go through the process, what we are doing, or our customers test, for example, powder metal parts to 100%, test car body parts to 100%, and even forged ceramic parts, something like that. Here, I only want to show you some basic thoughts about non-destructive testing. Important for non-destructive testing is process reliability. That means if there is a quite reliable process with small deviations between the parts, then also very small defects can be found. On the other hand, process reliability is quite important to mass production, and therefore you need a reliable fault detection. Of course, no pseudo rejects should be generated. And what is also important is detection of unknown faults. If we go, for example, back to this parts, the crack in this car body part can be very different positions. And so the behavior of every crack, every fault is different. And so the one requirement of the non-destructive testing system is to detect faults that never occurred before. Then, of course, 100% testing in the production is necessary. If you talk about safety relevant parts, if you talk about the car body parts, it doesn't make sense to test every 10th part, since then the probability that one of the cracks will not be found by the system is 90%, and nobody wants to live with that. So we have to do 100% testing, of course, otherwise we spend a lot of money with no effect. And of course, documentation is quite important. Our users of our quality testing systems not only are interested in detecting faults, but also to find the root cause, to understand what happens and to understand or to find a way how to avoid this. That means the documentation, the statistics, data stored to every item is quite important to be able to enhance the quality of the production. And that's also the advantage that such a system gives if you compare it, for example, with manual testing or whatever. Yes, the basics, it's quite simple. A part is excited so that the resonance frequencies can be measured. The resonance frequencies are affected by geometry, by density, by mass, by stiffness, by the elastic modulus of the part. And if one of these things change, then it will have influence on the resonance parameters. That means on frequency, level, and damping of certain resonance. And this can be detected by an intelligent analysis function, so that if there is a deviation from the normal behavior of the production, then it can be detected. And so a part can be detected which is different than all the other parts. And this system is also adapting to the production line, so that also in the production line, faults can be found that may be covered if the whole scatter of the whole production is taken into account. Those were the applications. Now, what do we provide? What can we provide to you to help you to ensure a high production quality? We provide a whole solution. The solution consists of hardware. This is a signal recording device. This can be a hammer to excite a part. Of course, the main part of this stuff is the software. In the software, all the intelligence is built in to detect a certain issue from the overall noise emitted at the test bench. We also provide the right sensors that fit to an application. The sensors are chosen together with the user to find the best solution. And if we talk about the solution, we also talk about engineering. It starts with technical consulting. We are used to talk with our customers from the first day on. If they tell us we have certain tasks to measure noise and vibration at the production line to provide a certain kind of quality testing, then we talk to our customers, do preliminary studies, make technical specifications so that we can specify a test system that can be used for these cases. Then, of course, we do the commissioning, training, and also after-sales support. We know that many of our customers are no NVH experts, and so we help them with our expertise to use NVH measurement testing system at the production line under the best conditions that are possible. Built-in robustness and reliability, this is valid for the sensors. They are designed for using at the production line, like this accelerometer, like the laser vibrometers. They are designed to work under these harsh environments. They are designed to test at high rotation speeds. They can be calibrated in situ. They can be automated, adapted. They are self-supervised so that a defect can be detected, so that it can be assured that the quality testing system at the production line always runs under good conditions. Also, the hardware is designed in a way that it can be built into a test bench quite easily. It has an Ethernet connection to the PC, so no special drivers are needed. It's a modular system with up-to-date signal inputs, up-to-date tacho inputs. It consists of optional modules for several applications, and it is available in different housings. As a DIN rail housing, small housing that can be clipped on the test bench, or bigger housing which is more flexible if more sensor channels are needed. And the system also can be easily integrated in the test bench. We provide interface for the most important PLC systems like Profinet, Profibus, EtherCAT, Industrial Ethernet, Digital I/O. And it can be integrated in a way that it's seamlessly integrated in the whole infrastructure of the test bench, so that sometimes the customer even does not see any window of the Novus software, and the system runs in the background for the 100% test. This is how it is implemented. The hardware talks with our software. There's a certain interface called Test Bench Control or Test Bench Connect that talks with the test bench software, so that the system is fully automatically controlled by the test bench. Yes, of course, the software also is modular so that it can be adapted to a new application by mouse click. That means at the end, we do not need to program anything. If we have a new application, we can click together our modules, the so-called flowlets, in a way that they fulfill the requirements of a new measurement task within some minutes, half an hour, 2 hours. That means no programming required. All the adaptation work is done during the normal commissioning. Yes, that means we provide you solutions for end-of-line testing to provide short cycle times, to do a parallel functional test at the test bench, to minimize false rejects, to find all the interesting faults at the production line. Also provide software to do offline analysis in the office, to do a more detailed root cause analysis, to do statistics, optimizations of the process of the test system itself. It can be integrated in quality management systems seamlessly. There's direct access by SimCenter Test Lab. SimCenter and Novus analyze capabilities can be integrated in the system so that we provide the whole loop of quality testing. And of course, we do this since some years. Our team is willing or is glad to provide our expertise to help you to build your testing solution in the most effective way. Thank you for your attention. I hope to get some interesting mails with some interesting questions, and I will be glad to answer them.